Swayam Prabha. Digital India. Educated India.
Welcome to lecture 9 of basic electrical circuits. In the previous lecture we looked at mesh analysis. It's an analysis method where you start with Kirchhoff's voltage law around different meshes in the circuit. It's a sub case of this loop analysis. So now we see that it's an alternative to nodal analysis, and as at the very end of the lecture we were trying to figure out which one would be used, nodal analysis or mesh analysis. Okay. So before we get there, if there are any questions about any of the previous lectures, please ask so we can discuss those things. Any questions about the previous lecture? Okay, in that case let's go ahead with the lecture. At the end of the previous lecture I asked whether we would use nodal analysis or mesh analysis. I say mesh analysis, so in general loop analysis. And the way to decide is that nodal analysis has n-1 KCL equations and loop analysis will have b-n+1 KVL equations, which you have to solve for a circuit with n nodes and b branches. Okay. So what we have to decide is n-1 a larger number or b-n+1 a larger number. Okay. So to answer this, I asked you, first of all, the number of branches depends very much on the circuit, but what is the maximum number of branches you can have? N node circuit, if there are branches between every node and every other node, that is, if there are branches connecting all nodes to all other nodes, how many branches will be there? Okay, please try to answer this question. How many branches will be there? Okay, there were a couple of answers saying 2n minus 1 and the other one was n times n minus 1 by 2, and that's the correct answer. The correct answer is that it will be n choose 2 or n times n minus 1 by 2. Okay, so every branch can be connected to n minus 1 other branches. That's why you get this n minus 1 here, and then you have n possibilities for selecting the starting node, and also you get divided by 2 because if node A is connected to node B, it's the same as connecting node B to node A. Okay. Alternatively, you can think of while adding branches, you have to pick 2 nodes. You have n possible nodes, and out of that you pick 2 nodes, and you can do that in n choose 2 ways. Okay, n times n minus 1 by 2. So this I will simply approximate it by n square by 2 for large n. Okay, so this n minus 1 is approximated by n. So if every branch is connected to, every node is connected to every other node by branches, this number b minus n plus 1 will be of the order of n square by 2, okay, for large n, and the number of KVL equations will be lot more than the number of KCL equations. Okay, now in reality it will be somewhere in the middle. It's possible that you have very few branches, that is you just have a single loop. Okay, for instance, you can have n nodes and branches only like that. In this case, clearly number of KVL equations will be smaller. Alternatively, you can have everything connected to everything else. Okay, something like this. Right? In this case, you have a lot more KVL equations than KCL equations. Now the reality will be somewhere in between. It's not that all the nodes will be arranged in a single loop, or it's not that every node will be connected to every other node using a branch. So the number of KVL equations will be smaller than this, but in general it tends to be a little more than the number of KCL equations. Okay, so that is one reason. Although this is not a hard and fast rule, and it's possible to have a single KVL equation for an n node circuit if you happen to have a single loop. In that case, you choose KVL. Now it turns out that this analysis of circuits using a computer, that uses nodal analysis. There is another reason for it. Okay, that is that it's very easy to identify nodes. They are just given to you. And this is true even for human beings. You look at a circuit, you know what the nodes are, but a little harder to identify all the loops. Okay, so you have to first identify a tree, then start adding links to the tree to form loops. Okay, so because of these reasons, usually if you want to do systematic analysis of large circuits, you end up using nodal analysis. Okay. Okay. Is the audio okay? Okay, it seems fine for some people, but maybe for those of you for whom the audio is not good, You have to check the setup at your end. Okay. So this is just to say that you end up using nodal analysis for systematic analysis of large circuits. Okay. So far what we have done is to look at nodal analysis and mesh analysis. We can systematically write down equations for the two cases. If you have only current sources and resistors, nodal analysis comes out with a nice structure. Similarly, if you have only voltage sources and resistors, mesh analysis equations have a nice structure. But either of these can be used even when you have other sources. That is, you can use nodal analysis when you have voltage sources and mesh analysis when you have current sources. In case of nodal analysis with voltage sources, you either define an auxiliary variable or use supernode. Similarly, in case of mesh analysis with current sources, you use an auxiliary variable for the voltage across the current source or use a super mesh. And when you have controlled sources, things tend to become more complicated, but you should be able to figure out those things as well. And if you are trying to solve some specific problem but run into some trouble, then please raise it in the class and we will discuss that. Okay. So any questions on either nodal analysis or mesh analysis? Any questions? Okay, then let's move on to the next topic in our course, which is certain theorems involving circuits. What I showed so far was ways of systematically analyzing large circuits. Okay, so that's how you use nodal and mesh analysis. Now when you are doing hand analysis of small circuits, you tend to use a number of ad hoc ways. In fact, I will discuss many of those things after I discuss the circuit theorems. Okay. So we will start with some very simple things first. Okay. First of all, these are not called circuit theorems, but some transformations that you can use, and we have already discussed these, but I will briefly touch upon them. If you have a voltage source in parallel with anything, it is the same as the voltage source. Okay. This is just to remind you of some basic results. Okay, so if this is V0, this will also be V0. And similarly, if you have a current source in series with anything, it is equivalent to a current source. Okay, I assume that there will be no questions about this. These are really basic results. Clearly, whatever element you have in series, the current coming out here will be I0. So current source in series with anything will be just a current source. Similarly, whatever this be, across this you have a voltage V0. So whether you analyze when I say equivalent, what it means is, if you analyze the circuit with this or without this, you will get exactly the same result. The only difference will be that this may draw some extra current from the voltage source. Okay, so except for the current in the voltage source, having this or not having this, there will be no difference. Similarly here, except for the voltage across the current source, having this or not having this will not make any difference at all. Okay. Now let's move on to slightly more sophisticated things. Now let's say we have a node with a number of branches, and this is the node. Okay, and this is branch number 1, 2, 3 and 4. Okay, so this is just an illustration, and let me assume that in my particular circuit in series with these 3 branches there happen to be voltage sources. Okay, and all of the same value V0. Okay, so all I am saying is there is a node, and in my example I have taken 4 branches, and in 3 of those branches there is a voltage source with the same consistent polarity and the same value V0. Okay, let's say this is the circuit. This is just the assumption. Now in general you can have n nodes with n minus 1 branches. Sorry, you can have one node with n branches, and n minus 1 of those n branches will have the same valued voltage source. Okay, so this is the circuit. So now what I would like answers from you is, let me call these nodes n1, n2 and n3. Okay, what will be the, how will be the voltages at n1, n2 and n3 be related to each other? My question is, there will be some voltage at n1 with respect to the reference node of the circuit, and n2 and n3. Okay, so how are these going to be related to each other? Please try to answer this. So the question is, how are the voltages at n1, n2 and n3 related to each other? So a couple of you have given your answers. They will be the same voltage, and that's pretty clear, because let's assume that the voltage here is some V1. Now the voltage at N1 will be V1 plus this V0, and here it will be V1 plus V0 again, and here also it is V1 plus V0. Okay, so they'll all be equal to each other. Now it turns out that if two nodes in a circuit have the same voltage, you can connect them without changing the circuit. Okay, so if you have two nodes and you know that the voltages are identical, okay, if this is V1, this is also V1, then you can short these two without affecting the circuit. Okay. Now this can be done in most cases, but there are some cases where it cannot be done. I will not go into them now, but in most most regular circuits you can do this. Okay. So what does this mean? Because the voltage here, there and there are the same, I can connect all of them together. Okay. And in fact, if I had more branches with voltage sources like this, I could connect all of them together. Okay. So now if I observe this circuit, I see that this voltage source and that voltage source and that voltage source are in parallel with each other. Okay. So these three voltage sources are in parallel with each other. Now if you have voltage sources of equal value in parallel with each other, first of all, if they are of unequal value, you cannot even connect them in parallel. But if they are of equal value and parallel with each other, it's the same as having a single voltage source. Okay. So this is the same as doing this with a single voltage source V0 and this branch number 1, 2, 3 and 4. Okay. And this node represents the union of the three nodes, basically whatever I have shorted, and you have a single voltage source. Okay. So what this whole exercise is showing is that if you have a picture like this with voltage source on one of the branches, it is exactly the same as having a picture like this with this voltage source moved to all the other branches. Okay. Any questions about this? Okay, so now this theorem is sometimes useful to prove other theorems. We may not use it directly in this course, but this is known as pushing the voltage source through a node. Now I proved it by starting with these multiple voltage sources and combining them into this one, but it's usually more useful to go the other way around. If you have a voltage source in a single branch, you can push it into all the other branches connected to that node. Okay, so typically you end up going in this direction, and this is you can call this as pushing a voltage source through a node. Okay. So this is about voltage sources, and similarly for current sources there is something. Okay. Now let's say you have a current source I0 in a circuit. Okay, and it's exactly the same as having two current sources in series of identical value. Okay, so this by definition is exactly equal to that one. Okay, now if we have formed a new node in the middle, and if you take a wire from that node, what will be the current flowing here? What is that current going to be? Whatever be the value of I0, any current source, you take it, split it into two sources in series and form a node in the middle, and if you connect a wire to that middle node, what will be the current flowing through that wire? Yeah, it's pretty clear that this Ix will be 0. Okay. So now this is useful in the following way. Because the current here is identically going to be 0, you can take this node and connect it to any other node in the circuit. Okay. Okay. Now this is sometimes useful. So if you have a current source connected between, let's say, some nodes N1 and N2, you can split that into two current sources and you can connect the middle to anywhere, and usually it's convenient to connect it to the reference node. Okay. So instead of a single current source between N1 and N2, you will have a current source from N1 to the reference node and from the reference node to N2, and sometimes this is easier to analyze. Again, I will point out if there are examples that make use of this, but this is some general property that you can use to simplify circuits and visualize certain things about circuits. Okay. Any questions about this? Okay, so these are quite simple, so we can move forwards. Now the next thing is a little more interesting. Let's say I have any circuit N. Okay, any circuit or network N, and there is some element connected to it. I will take a resistor as an example, but this can be any element. Okay, and it doesn't even have to be linear. So let's say I have a resistance R, and this has all kinds of things in it. It can have resistors, current sources, and voltage sources, and so on. Okay. Now the question is, okay, can I take this circuit, remove the resistor and put something else here, okay, some box, such that all the voltages and currents in this circuit are exactly the same as voltages and currents in this circuit. Okay, let me assume that in the original circuit there is a certain voltage across the resistor and there is a current through the resistor. Okay, so under these conditions, can I replace the resistor with something else so that all the solution to the circuit, that is all the branch voltages and branch currents in this circuit, will be exactly the same as the ones in this circuit? Is that possible? If so, what will I replace it with? Please try to answer this.